What happens inside a black hole? Part 1. Tonight, allow your thoughts to slow down and settle. There is no need to imagine distant civilizations or fictional adventures. Instead, we will explore one of the most fascinating mysteries in modern science, a mystery that exists not in fantasy, but in the real universe itself. Black holes. These strange objects are among the most extreme things ever discovered. They cannot be seen directly. They emit no light. They hide behind a boundary from which nothing can escape, not even light itself. Yet despite their invisible nature, black holes shape galaxies, bend space and time, and challenge our understanding of reality. Our story begins with a star. Not an ordinary star like the sun, but a giant star many times more massive. Stars spend most of their lives converting hydrogen into helium deep inside their cores. This process releases enormous amounts of energy. The outward pressure from that energy balances the inward pull of gravity. For millions of years, sometimes billions, this balance remains stable. Gravity pulls inward, energy pushes outward. The star survives. Eventually, however, fuel begins running out. The star changes. New elements form inside its core. Helium becomes carbon. Carbon becomes heavier elements. Layer after layer develops within the star, like the layers of an onion. The process continues until iron begins accumulating. At this point, something important happens. Iron cannot produce energy through normal fusion, the way lighter elements can. The star reaches a dead end. Suddenly, the delicate balance between gravity and pressure starts collapsing. Gravity wins. Within seconds, the core begins falling inward. Matter rushes toward the center at incredible speeds. Temperatures rise. Pressures become unimaginable. The collapse accelerates. Then, in many cases, the outer layers explode outward in a brilliant supernova. For a brief period, the dying star may outshine entire galaxies. The explosion spreads newly created elements throughout space. Many of the atoms that make up planets, oceans, and even human bodies were originally forged inside stars like these. But what remains after the explosion? That depends on the star's mass. Smaller stars may leave behind neutron stars. The largest stars leave something even stranger, a black hole. Imagine compressing enormous amounts of matter into an incredibly tiny region. Gravity becomes stronger and stronger. Eventually, it becomes so powerful that space and time themselves are dramatically distorted. This is where the black hole forms. At its center lies a region called a singularity. Scientists do not yet fully understand what happens there. The mathematics predicts a place where density becomes infinite and known physics breaks down. Whether singularities truly exist exactly as described remains one of the greatest unanswered questions in science. Surrounding the black hole is a boundary called the event horizon. This is often described as the point of no return. Anything crossing this boundary can never escape. Not matter, not light, not information, at least according to traditional understanding. From outside, the event horizon appears almost simple. Crossing it would not necessarily involve hitting a wall or passing through a visible barrier. Instead, it marks a location where gravity becomes so overwhelming that every possible future path leads inward. Imagine floating safely far away from a black hole. The object itself appears dark, invisible, yet its presence becomes obvious through its effects. Nearby stars move differently. Gas spirals inward. Light bends around it. The black hole reveals itself by changing the behavior of everything nearby. One of the most remarkable predictions of Einstein's theory of relativity is that gravity affects time itself. Near a black hole, time passes differently. The stronger the gravity, the slower time flows compared with distant observers. This phenomenon has been measured throughout the universe and confirmed repeatedly. Near Earth, the effect is tiny. Near a black hole, it becomes enormous. Imagine two clocks. One remains far away. The other approaches a black hole. When compared later, the clock near the black hole will have experienced less time. From the perspective of a distant observer, events near the event horizon appear to slow dramatically. An object falling inward seems to move slower and slower. Its light becomes increasingly redshifted. Eventually, it fades from view. The object never appears to cross the horizon. Instead, it seems frozen near the edge. Yet from the falling object's own perspective, something very different happens. Time feels normal. The journey continues. The event horizon is crossed. The black hole accepts another traveler. This strange difference between perspectives remains one of the most fascinating consequences of relativity. The universe does not always behave according to everyday intuition. Space bends, time stretches, reality becomes more complex than simple experience suggests. As our journey continues, we move closer toward the event horizon. Not physically, only in thought. Scientists have spent decades studying what might happen here. Powerful telescopes observe black holes throughout the cosmos. Computer simulations model their environments. Equations attempt to describe regions where gravity becomes almost unimaginably strong. Yet despite all this knowledge, one enormous mystery remains. What actually happens inside? That question continues waiting in the darkness. What happens inside a black hole? Part 2. The question remains. What happens after crossing the event horizon? Surprisingly, science does not yet have a complete answer. Black holes represent a place where two of humanity's greatest theories collide. Einstein's theory of general relativity describes gravity with extraordinary accuracy. Quantum mechanics describes the behavior of particles and energy with equally impressive precision. Both theories work remarkably well, yet inside a black hole, they appear incompatible. Physicists have spent decades trying to reconcile them. The mystery remains unsolved. As we continue our journey, imagine approaching a black hole. Far away, gravity feels normal. Closer, it grows stronger. Closer still, something unusual begins happening. Different parts of your body experience different gravitational forces. The side closer to the black hole feels a stronger pull than the side farther away. This effect is called a tidal force. Near Earth, tidal forces from the moon help create ocean tides. Near a black hole, tidal forces can become extreme. For smaller black holes, they may become fatal long before reaching the event horizon. The stretching effect grows stronger and stronger. Physicists sometimes call this process spaghettification, an unusual name for a very serious phenomenon. Objects become stretched in one direction and compressed in another. Matter itself is pulled apart by gravity. For a small black hole, this would happen rapidly. For a supermassive black hole, however, the story is different. At the center of galaxies exist black holes millions, or even billions of times more massive than the Sun. Their event horizons are enormous. A person crossing such an event horizon might initially notice nothing unusual. No visible wall, no sudden shock, no dramatic flash. The crossing could happen quietly. Only later, deeper inside, would gravity become increasingly destructive. This leads to a fascinating realization. The event horizon itself is not necessarily the dangerous part. The real danger lies deeper within. And deeper within is where the greatest mystery waits. According to Einstein's equations, every possible path eventually leads toward the center. Escape becomes impossible. The singularity lies ahead. But what exactly is a singularity? Mathematically, it represents a location where density becomes infinite and known physical laws cease functioning. Most physicists suspect that this description is incomplete. Infinite quantities often signal that a theory has reached its limits. Nature may behave differently than the equations suggest. Some unknown theory of quantum gravity may eventually reveal the truth. For now, however, nobody knows. The singularity remains hidden behind the event horizon, forever inaccessible to direct observation. This creates a unique scientific challenge. Normally, scientists test ideas through experiments. Black holes make experimentation difficult. Information from inside cannot return. The universe effectively hides the answer. Another mystery emerges from this fact: the information paradox. Imagine throwing a book into a black hole. The book contains information, words, ideas, patterns, everything describing the book's contents. What happens to that information? Classical physics suggests it disappears behind the event horizon. Quantum mechanics disagrees. According to quantum theory, information should never truly be destroyed. This disagreement created one of the most famous problems in modern physics: For decades, researchers debated possible solutions. Then another surprising discovery complicated matters even further. In the 1970s, physicist Stephen Hawking demonstrated that black holes are not completely black. Quantum effects allow them to emit tiny amounts of radiation. Today, this phenomenon is known as Hawking radiation. The process is incredibly slow. For large black holes, the radiation is extremely weak. Yet over immense periods of time, it has profound consequences. A black hole can slowly lose mass. Eventually, after unimaginable lengths of time, it may evaporate entirely. This raises another question. If the black hole disappears, what happens to the information that fell inside? The puzzle remains one of the greatest challenges in theoretical physics. Different ideas attempt to solve it. Some researchers suggest information is somehow encoded on the event horizon itself. Others propose new quantum processes that preserve information in subtle ways. Still others believe our understanding of space and time requires fundamental revision. One particularly fascinating concept emerged from studies of black holes, the holographic principle. According to this idea, information describing a three-dimensional region may actually be encoded on a two-dimensional surface. The concept sounds almost unbelievable, yet it appears repeatedly in advanced theories of gravity and quantum mechanics. Some physicists even speculate that the entire universe may operate according to principles similar to a hologram. Whether this idea is ultimately correct remains uncertain, but black holes continue providing clues. They serve as laboratories for the deepest questions imaginable. Questions about reality itself, questions about space, questions about time, questions about existence. As we move farther into the future, powerful observatories continue studying black holes. Scientists have already captured images of the shadows cast by supermassive black holes. These observations confirmed predictions made decades earlier. New telescopes promise even greater discoveries. Perhaps one day humanity will develop a complete theory combining relativity and quantum mechanics. Perhaps the secrets hidden behind event horizons will finally become clear, or perhaps black holes will continue surprising us. The history of science suggests that nature often proves more creative than our expectations. For now, black holes remain among the most mysterious objects in existence. They sit quietly throughout the cosmos. Some drift alone through interstellar space. Others occupy the centers of galaxies, including our own. At the heart of the Milky Way lies a supermassive black hole called Sagittarius A*, invisible, silent, yet containing millions of times the mass of the Sun. It has existed for billions of years. While Earth formed, while life evolved, while dinosaurs appeared and vanished, while humanity emerged, the black hole remained, a silent presence at the center of our galaxy. Tonight, as our journey comes to an end, imagine looking out across the universe. Stars shine in every direction. Galaxies drift through the darkness. Nebulas glow softly among the stars. And scattered throughout this immense cosmic landscape are black holes, invisible yet powerful, hidden yet influential. Objects that challenge our understanding of reality itself. We may not yet know what truly happens inside them, but perhaps that mystery is part of their beauty. The universe does not reveal all its secrets at once. Some answers require patience, some require new discoveries, and some continue waiting in the darkness beyond the event horizon, where space bends, time slows, and one of science's greatest mysteries quietly endures.